My name is Lubos Nahlik, and I would like to say a few words about our research devoted to fatigue rate propagation and railway access. I am coming from Institute of Physics of Material, which is part of the Academy of Sciences. And we have a long-lasting cooperation with Bonatrans company, which is huge producer of railway access and railway resets. So we take part in the, let's say, developing process of this company as well. I will talk about lifetime of fatigue lifetime of railway access. So in our design process, we assume existence of some initial crack. The size of the initial crack is, let's say, limit size of crack, which can be recognized by non-destructive testing methods. We usually assume that this initial size is about 2 millimeters. During years, we have developed quite sophisticated procedure how to estimate lifetime of a railway axle. I will go briefly through this procedure. So we have to take a real geometry. We have to consider a real geometry of axle and the wheels and other parts, and then we find by some basic finite element analysis, let's say critical spots, critical places on the axle surface. We consider loading spectra. What is important part of the analysis to know the distribution of residual stresses across the cross section of the axle. Then we prepare finite element model with cracks, and we simulate crack propagation in the axle. What is important part is to know well material characteristics for a crack propagation. We consider some retardation effect, and for the final calculation of lifetime of the axle, we usually use an Nesgro approach or some modification of this approach. So, what is important for simulation of crack growing through the axle is to consider a real crack shape, because the crack shape changes its geometry during propagation, and we have to take into account this change. In this procedure, we took into account press fitted wheels and the residual stresses due to press fits. We consider residual stresses due to manufacturing processes, for example, due to technological processes, for example, due to hardening of the axle, and so on. For our calculations, we usually use stress intensity factor as a quantity describing the stress concentration in front of the crack tip. What is necessary to know crack growth rate for the different R ratio? We usually measured crack growth rate for different loading ratio, usually from -2 to 0.8, because there is several reasons. There is press fit load inside the axle, different amplitude loading, and residual stresses from technological processes. Today, I would like to speak more about the effect of humidity on fatigue crack growth. So we have developed, let's say, at house our small chamber for empty specimen, so we are able to measure the crack growth rate under, let's say, laboratory conditions or in this chamber, where we can decrease air humidity in this chamber. Here you can see important results from this part of research. It is change of threshold values of stress intensity factor for, let's say, normal laboratory air and for dry air. This decrease of threshold is very important and can influence the result lifetime of your estimation. So I have prepared some, let's say, example how the humidity can influence residual fatigue lifetime of a railway axle. We chose, let's say, two cities where the weather during the year plays important role, Chicago and Beijing. So for let's say, summer condition, the measured values of stress intensity factor is about 13. For winter conditions, it's about 10.5 megapascals square meter. So you can see the important difference between these volumes. So there is, let's say, a bit funny table, but I would like to show you the importance of the weather conditions in your estimation. So we calculated a lifetime by our procedure for summer conditions. Summer is, let's say, referent value 100% of lifetime, and for winter conditions, and you can see important decrease of residual fatigue lifetime of the axle for cities where is cold weather during winter, for Chicago or for Beijing as well. So the decrease is important. The lifetime is more than 10 times lower than let's say under summer conditions. What is the explanation of this effect? The explanation, or it is caused by oxide debris developing on the crack faces during crack growth. And in dry air, there are no conditions for developing of oxide debris, but on, let's say, normal air humidity, there develop oxide debris, and these oxide debris causes earlier closing of the crack during its propagation, and it decreases the threshold volume. We have observed this fact in electron microscopy. There were no evidence of oxide in let's say in dry air, and quite important 90 nanometers of oxide in normal humid air. So everything, as I said, we cooperate in the design process and developing process with Bonatrans company. So with this fact, we decided to do one-to-one scale test in Bonatrans. As I said, and it is the different part of this story, we have to know the distribution of residual stresses through the axle. I cannot speak about it in details, but everything is written in this paper. So important closing stress which closing the crack. Here you can see real geometry of the axle, experimental stand loaded by retention bending. at this amplitude 165 megapascals. And during winter condition with, let's say, lower air humidity. We applied all our procedures and put all parameters necessary for calculation or estimation of lifetime. And here you can see the correct Excel and comparison between experimental values, let's say blue values, blue markings, and simulations. And you can see that it corresponds very well. To conclude my talk, I would like to say that we have developed some procedure for lifetime estimation of railway excess. It is important to, when you measure in laboratory threshold values, to consider real application of your data. And if we are talking, for example, about application behind the polar, in polar areas and so on, it's good to know that there is important shift down of the threshold values, and it is necessary to consider this lower threshold for fatigue rate propagation. So thank you very much for your attention.
Thank you.